Yes, sorry about that. This is the real formula. It's gamma of n. Now let's to see why this depends on n. The reason it depends on n is that you look here and you see a dependence on x. But that dependence on x disappears when you take the integral. It's like a summation. It works the same as a summation. You know, if I say take the sum I goes from 0 to 3 of I. Now what is that? It's 0 plus 1 plus 2 plus 3. Do you agree? When I is 0, then I is 0. When I is 1, then I is 1. You know what I mean? When the index is 0, then I is 1. When the index is 1. Now what is this number? It's 6. Do you agree that this has got nothing to do with I? The index of summation has disappeared. That always happens with summations. The index of summation is never in the answer of the summation. And it's the same thing with integration. The index of integration, which is the variable of integration, if you actually do the integral, it's not there anymore. It's like a dummy variable. This x is only there so that you can take this e to the minus x and this x, add up a whole bunch of rectangles. The way to think of it, it's like a dummy variable. It's called the index of integration. It could be anything. In other words, if I didn't write x here, if I wrote u, and then I'd have to put a u up there, and then a u down there, the function is exactly the same. I haven't changed anything. But all of the dependence on u will disappear when you add up all the area along the line of u. Okay, now first of all, the reason why this is such an amazing invention is because you have to kind of be extremely smart, or you have to be very inspired, or have a moment of a flash of insight in order to come up with this. Once you come up with it, I mean, look, you can think about it for a while. You can fiddle with integration by parts for a long time, and you can start to see that something like this is waiting to be discovered. If you play around with integration by parts for a long time, you will notice that there are weird things you can do. You can make functions, you can define functions in terms of themselves and stuff like that. And then that's when you notice, maybe I can do something recursive here. But it still takes a great leap of genius to come to this conclusion. The next thing is, you can't just do the indefinite integral. You know, this is an antiderivative. You see, I don't have limits here. It's an antiderivative, no limits. But if you do that, the answer doesn't come out the way you want. You can't make it an actual antiderivative. You can't make it an indefinite integral. You need to make it a definite integral. In other words, you actually have to work out a real area, not just an antiderivative. And the answer is to do this. Now, if you're wondering, how can you do that? How is that legal? Well, it's legal because what you're really doing is you're saying an integral from 0 to some number. Pick your favorite number. Let's call it x. Doesn't matter what you call it. You're saying, actually, I want to do the integral from 0 to x of this function. That's perfectly legal. We're going to stop at x. But then once you have your answer, you take the limit as x goes to infinity. That's what that actually means. It means you first compute the integral with a number, with nothing wrong with that. Then you take the limit of that as x goes to infinity. Okay, so if you do integration by parts, do you see what you get? Integration by parts, I mean, you have to. If you do integration by parts, worry about your calculator. If you do integration by parts, you can be clever. Remember what integration by parts tells you. It tells you that you need to choose something to be f dash and something to be g. Once you've chosen it, if you want to know what its integral is, it's simply f times g minus, swap the dash, f g dash. That's what integration by parts tells you. Okay, so there's not much going on there. We just need to pick something to be f and something to be g. Now, you have to make the choice wisely. I think I'll let this be g, because I've done it before. And you know, that's how I know. You let that be g, and you let that be f. Okay, now what does the rule tell us? The rule tells us that, f dash. The rule tells you that integral of f dash times g equals f times g minus the integral of f g dash. By the way, I know this is g and f dash. It's the same as f dash and g, because they're just being multiplied. You know, the order is the same. You can swap that g and the f dash to here. The order doesn't matter because it's multiplication. Okay, now let's work out what this is. So this thing here, then, according to this rule, if we call this g and if we call this f dash, then this becomes f, which is the integral of e to the minus u, with respect to u. Okay? By the way, u is the variable of integration. So when you integrate this thing, because I'm changing it from an f dash into an f, I could very easily, not very easily, but this wouldn't be a crazy thing for me to ask you to calculate, by the way, in integration by parts. The genius part is noticing that it does this. The genius part is not actually just working out what it does. Now, anyway, so if this is f dash, then what I need to write here for f needs to be the integral of this thing. Does that make sense? Mm-hmm. So if this is e to the minus u is f dash, well then f is just e to the minus u integrated. You can think about it for a bit, especially if you remember the information that d by dx of e to the x is just e to the x. Okay, so what if you put a minus up there? If you put a minus up there, the chain rule tells you that it's still e to the x times minus 1. Because the minus from up there has to be put as a chain rule factor next to it. Okay, so then e to the minus u. So what is the derivative of e to the minus u? The derivative of e to the minus u is minus e to the minus u. That's the derivative, not the integral. That's the derivative. Okay, what's the derivative of this? What's the derivative d by du of this? Well, you just get another minus in front. Do you see, every time you differentiate an exponential function, it stays the same. You just need to do the chain rule to it, which in this case gives you a minus. So you just get another minus in front, which is back to e to the u. You see, it takes you back there. In other words, the integral of this is also that. This is an interesting function. Its derivative and its integral are the same thing. It's this. When you differentiate this, you get that. And when you take that and differentiate it, you get back what you started with. So this is an example of a function where integrating it and differentiating it are, well, I won't say it gives you the same thing, but its integral and its derivative are the same. You can think of the picture like this. Start with e to the minus u. You differentiate, you get minus e to the minus u. You integrate, if you integrate, you get back there. If you integrate minus e to the minus u, you get e to the minus u. If you differentiate, you get minus e to the minus u. That's all by the chain rule. The chain rule does all of that for you. Everything has the chain rule. However, what happens if you differentiate this number? If I take this number and differentiate it, what happens? Oh look, I also get there. If I differentiate this, the chain rule takes me to the same place. And if I integrate that, it takes me to the same place. So it's a weird function where differentiating and integrating does the same thing. Anyway, we can fill it in here. It's minus e to the minus u. That's f. And g is u to the power of n. Okay? And n can be pretty much any number that's not 0. You know, if you make n 0, then you might have some problems here. But, okay? Now we integrated this, didn't we? Do you agree that this f is an integral of f dash? Yeah. And g is just g. But there's no more integral sign here. We don't write an integral sign again. That's the power of this method. The integral sign has disappeared here. The problem is, it's a definite integral. So we have to evaluate it at those numbers. Because it's a definite integral, when you get this integral sign disappearing, you have to evaluate it at the limits of the integral. It's always like that. Whenever you have a definite integral, like this is a definite integral. If the integral sign ever disappears, you've got to evaluate it. Okay, so we'll come back to that. Minus what? Minus the integral, and we're going to do this part, of f, which we already worked out was minus e to the minus u. We worked that out, right? That's f. It's the same f as this. This f is that f times g dash. What's g dash? Well, g is this. It's u to the n. Right? G is equal to u to the n. Therefore, what is dg by du? In other words, when you differentiate this with respect to u, and why am I doing that? Because look over here, here's a g dash. I'm trying to work out g dash. So if that's g, then what's g dash?
N u to the n minus 1.
Indeed, exactly. N u to the n minus 1. And that's the part where if you see this is where the genius starts trickling in. When you see that, you go, hang on a second, look what's happened. I've brought the n in front, and the dependence on n has dropped by 1. That sort of is like a factorial, except the problem is, it's a lot like a factorial, but the problem is that it's going to disappear unless you can latch onto something that doesn't disappear, and that's what all the rest of the stuff is for. The rest of the stuff is to stick it onto something that doesn't disappear. Here's the thing that doesn't disappear. This would eventually disappear if you kept doing it enough. But you don't want it to disappear, you want it to keep having this behavior every single time. So you stick it on the end of this. So let's put it there. It's n u to the n minus 1. Okay? What integral is it? du, don't forget that. Since it's du, we're allowed to pull out everything that doesn't have to do with u. Right? Anything in this integral that doesn't have to do with the variable can come out. For instance, I can make this into a plus. Take the minuses out. I can also take the n out, right? N doesn't have anything to do with u. So I can take the n out. And that's all I can do, I think. Okay. In the meantime, let's evaluate this. What do I get? Let's just quickly, we'll do it over here. When I have to say what I get when I put infinity in, so it's minus e to the minus infinity times infinity to the power of n. That's when I put infinity into u. Right? Use the variable, so it's minus e to the infinity to the n, minus, that's what I get when I put infinity in. What do I get when I put 1 in? I get minus e to the power of 1 times, oh, not 1, 0, sorry, yeah, times that, times 0 to the power of n. Okay, so this isn't, you have to think about it a bit, but this bubble is what you get when you try to evaluate this real thing. This disappears, I hope you agree, right? Because there's a 0 there. 0 to the power of n, that goes away. This one you have to think about for a bit, because it's e to the minus infinity times infinity to the n. Now, you can consider on an individual level, what is e to the minus infinity? It's equal to 1 over e to the power of infinity. Right? 1 over e to the power of infinity, if you're working with limits, is 0. It's basically 1 over some huge infinity. If you're working with limits, you could say that. So this is 0. But you've got 0, what happens to infinity to the n? Infinity to the n is just infinity. So you've got a problem over here. This minus e to infinity times infinity to the n is a indeterminate form, if you remember. We learnt about that when we did limits. This little thing over here, this blob, that piece there, and by the way, we can get rid of the minus because that's the 0. This little blob here is an issue. If you try to evaluate it, you get negative infinity times, sorry, you get, not negative infinity, you get 0, as we worked out, it was 0, not negative infinity. You get 0 times negative infinity. Now that's an indeterminate form, if you remember. 0 times infinity, when you're using limits, means you don't know the answer. It could be anything. So I won't show you how to do it now, but there's an argument you can go through where you say, okay, who gets to where they're trying to go faster? Does e to the minus infinity head towards 0 more quickly? Or does infinity to the power of n head towards 0 more quickly? And the idea is that exponential functions always win. Powers, it could be an infinite power, like meaning it could be a big power. It doesn't matter how big the power is. An exponential function always will eventually be bigger than a polynomial. So in other words, this guy is going to win. The e to the minus thing is going to win. And if he wins, then it means 0 wins, and this all just goes away. It was 0 minus 0. Did you see how we did that sort of thing? Once you agree that e to the minus infinity goes to 0 more quickly than infinity to the n goes to 0, once you kind of, it's not, you don't have to agree, there is an argument for this, a very sound argument, but we'll take off another board, to see that this person heads to 0 more quickly, this person heads to 0 faster than this person heads to infinity. So the 0 wins. So you end up with the whole multiplication between them giving you 0. because the 0 wins the race to infinity. Which leaves you with that whole previous thing written here was actually just 0 minus 0. So it's 0. Okay, now look what we've got here. We've got n times something. Now let's compare this something to the gamma function. Let's compare. There's a u, there's a u. There's a e to the minus u, there's a e to the minus u. What's the difference? The only difference is that this one has an n minus 1, this one has an n. So you should notice, there's a bird there. Look, you should notice, the idea here is you should notice that this thing here in the block is exactly the same as this. The only difference is that instead of an n, it's got an n minus 1. You see the e to the minus u is there, the u is there, the du is there, the integral sign is there, everything is there. The only difference is instead of an n, you've got an n minus 1, which means that this thing in the block is actually gamma of n minus 1. If this is gamma of n, well, I mean, think about it. Take this, take the n, make it into an n minus 1. Well, then it becomes an n minus 1, which is exactly what we have there. And you can kind of see, right, what happens. Look what we've got. There's still an n we didn't write. N. So there you go. You proved that gamma of n is equal to n times gamma of n minus 1. And now whenever you have a function like this, it will work. It means what this implies, essentially, and prove the whole thing, is if I ask you, what's gamma of 6? You'll say to me, it must be 6 times gamma of 5. Right? Do you agree that's what we just showed? It's always that. Okay? Well, what's that equal to? It's equal to 6 times 5 times gamma of 4. It's going to keep doing this behavior. And you see, this behavior is like this behavior. But this thing would have disappeared by now. But we've still got the gamma function there because we stuck this clever e to the minus u on the back. Now this gives you 6 times 5 times 4 times gamma of 3. You can keep going, I'm sure you can imagine. It becomes 6 times 5 times 4 times 3 times 2 times 1 times gamma of 0. And gamma of 0 is actually quite easy to evaluate because if you take 0, put it in the gamma function, right, make n equal to 0. Well, u to the power 0 is just 1. Okay, and the integral from 0 to infinity of this, you can do whatever you do need to evaluate it, it's 1. If you put in the limits, if you do this integral and put in the limits, you get 1. So what's this? 6 times 5 times 4 times 3 times 2 times 1 times 1, that's 6 factorial. And we started with gamma of 6. So it turns out that this gamma function does everything that a factorial needs you to do, but it's continuous. And it can tell you strange things. It can tell you gamma of a half, which is kind of like asking the universe, what would a half factorial be? It would be that. It's a weird number. It would be a complex number, by the way. And what's the other thing? Oh, gamma of negative numbers. You can say, what's minus 2 factorial? Well, no one knows, but you could say that it must be gamma of minus 2. Put minus 2 in there, get a computer to do it, you'll see the answer. So, okay. I hope this demonstrated something to do with integration by parts to you. Do you think it did? Yeah, it can be, integration by parts can be a mission, but if you practice enough, just for the purpose of this video, I guess, because if people are watching, I'll give you an example to actually try. Not something this crazy, maybe do an easier one. Let's try something like this. Integral of x e to the x. There we go. That's an easy one. So I ask you to evaluate this integral. Okay. Evaluate. Okay, it's not, first of all, it's not a definite integral. You see I haven't put numbers there, so it's not definite. Yeah, there's not much more to say about it. X is the variable, there are no limits of integration. Now this is a sort of an easy one. It's an easier one. What would make you think to do integration by parts? If you ask, first of all, you try to do integration by u substitution. Is there anything you can see here where its derivative is nearby? I can't. the derivative of this is 1, and for the record that doesn't count, because you always find a 1, wherever you want to find a 1. So if the derivative of things is 1, that won't work. The derivative of x up here is also just 1, it's not x. The derivative of e to the x is e to the x. So nothing here can be derived to give you anything else here. None of the things, none of the factors, none of the terms you see can be differentiated to give you one of the other ones. So that won't work. You rather do integration by parts. Now you have to decide what to make f and what to make g. Well, let's say I just go without thinking. Make this f dash and I make this g. Remember, you don't make one f and g. I'm speaking incorrectly. You make one f dash because the formula has an f dash in it. It doesn't mean it's going to be differentiated. It doesn't mean it's already been differentiated. It just means we're going to look at it as if it's an f dash. Because every function is a derivative of some other function. And every function is an integral of some other function. You can, if you choose to look at it that way. So let's just do it blindly and go like this. Okay, what happens? The rule tells you that the integral of f dash g, which is now going to be this, right? We're calling this f dash, and there's the f dash, we're calling this g, so that's g. It's equal to f times g minus the integral, and now you swap the order of f g dash. Okay, what's that equal to? F. F is the integral of this, right? F, don't forget, f is supposed to be the integral of f dash dx. That's like kind of an obvious statement, but I guess this is the fundamental theorem of calculus, really. If you take the derivative of a function and then you integrate it, you get back the original function. So to go from f dash to f, you have to integrate. So what do you get? You get x squared times a half, times g, so it's times e to the x. No more integrals, minus the integral of f, we've already worked it out, there it is there, half x squared, times g dash. That's g. So what's g dash? Same thing, e to the x. When you differentiate, if that's g, then g dash is g. This g has the special property that g dash equals g. The derivative equals. Okay, here's our new thing. This is fine. Do you see there's no more integral sign here, so we're fine. Here's an integral sign, and can you see what's happened? It's become worse. Look at our original problem. X, e to the x. We've turned it into x squared e to the x. We've made it worse. This is harder to integrate than this. The reason is I chose these things badly. We try to choose it the other way around. Make this g and make this f dash. And let's see what we get using the same rule. We get f, which is the integral of this, which is just e to the x by the same reasoning as we did before, times g, which is just x, minus, okay, and we're done here, right? So it's f, integral of that is just that, charge g, okay, that's fine, minus the integral of f again. If that's f dash, then f is e to the x. It's the same as this. G times g dash. What's g dash? That's g, so what's the derivative of g?
1.
Yes. If it helps you to write out, you should write it out. If you write out, what did I decide? I decided to let g equal x. That's the decision I made. And you can write it out if it helps you to remember that's the decision you made. Now, if that's true, then what's the derivative of g dash? The derivative of g dash, to write it out explicitly, is dg by dx. If that's g, then dg by dx is equal to d by dx of just the function x by itself, which is 1. So I don't even have to write the 1 there. I can just put a dx. Now do you see, because we chose the f and the g the right way around, instead of it becoming more complicated, it actually became simpler. Can you see the x has gone away? It derived itself away. It turned into, instead of turning into an x squared, because we chose it the wrong way around, it turned into a 1, because we chose it the right way around. Now this is actually quite easy. This is e to the x times x minus, what's the integral of e to the x dx? It's e to the x dx again, because the derivative and integral are the same. And there you go. What is the answer? Easy. Not so bad. Through integration by parts. And yes, I don't think you wouldn't be able to do this without an integration by parts. I don't think. There's no way to do this by inspection. I mean, when you look at this, it seems so simple that you think to yourself, maybe I could have just spotted that. This answer is so simple that maybe I could have just spotted that this is the thing I can differentiate to give me that. The reason why it's not that simple is if you're trying to differentiate this, and let's take this quickly and differentiate it, d by dx, to check. Because if you thought, well, I'm very smart, surely something so simple, I could have spotted that its derivative would give me that. The problem is you have to do the product rule, so it's not as simple as you think. If you differentiate this, what do you get? Okay, let's do the product rule. You get this thing left alone times this thing differentiated, which is just e to the x, I hope you can see. It's this thing left alone, there it is, times x minus 1 differentiated, which is 1, plus this thing differentiated, which is e to the x, times this thing left alone, x minus 1. You add these two together, right? You get the like terms. It's e to the x plus e to the x minus 1. Can you see quite quickly that it's equal to e to the x times x? Because, well, basically you're subtracting one of your e to the x's, but then you're adding it back on again. So it's e to the x. I mean, you can multiply this out quite easily if you want to put it as e to the x times x minus e to the x. I just multiplied out the brackets in that case, and in that case, it cancels and you get that. And that was the original thing. So, the integration by parts is amazing. Yeah, there you go. Okay, the end.